To conclude our section on binary search trees, let's talk a little bit about how they are used in practice and what their performance is like. Binary search trees and variations of them are used very often to store data because, as their name suggests, they are very fast to search through and retrieve data from. In fact, it is also a very quick process to insert and delete data from a binary search tree. The reason for this is that all of these methods are basically implementing binary search, which we discussed in our lecture on time complexity and big O notation in section 1. If you are looking for a value in a binary search tree, you are going to start at the root node, like we did in our contains method. With every step that you take to a child node, you are throwing away half of the nodes in the tree. So you don't have to search every node in the tree. In fact, you search far less than every node in the tree. In a balanced binary search tree of 4,000 nodes, it only takes about 12 steps to find the node that you are looking for. If you remember, this is called a logarithmic runtime, and it is written as O of log n in big O notation. This is faster than the runtime of a linked list, which is O of n for searching, because in a linked list, you might have to search through every node in the list, or n nodes, to find the one that you are looking for. In a linked list of 4,000 nodes, you might have to search through all of them to find the one that you are looking for, but in a balanced binary search tree, you only have to search through about 12. That is a big difference, especially when the numbers start becoming a lot bigger than 4,000, like 4 million. Now, one important thing to note is that binary search trees are only this performant when they are balanced. To have a balanced binary search tree is to have one in which all, or most, of the nodes have a left and right child, so you have a full tree. In some strange cases, depending on the data you are using, you could wind up with every node only having a right child, for example. Then you would essentially end up with a linked list structure, and you would have to search through every node just to find the one you are looking for. So it is important to remember that binary search trees are most performant when they are balanced. Some practical use cases of binary search trees can be basically anything in which you might perform binary search. They would be a great data structure to implement a dictionary, a phone book, or anything else of that nature that involves binary search. They would also be a good data structure to store users of an application in if the users are stored by a numerical ID, because through binary search you could very quickly find a user that you are looking for. That is it for our section on binary search trees. I hope that you learned a lot and feel very proficient at implementing them in code. In the next section, we will explore our final data structure, a very powerful one, called the hash table. See you in the next section.